This video we will be discussing the ideas of related rates and doing some application problems. Notice that it tells us with related rates that we need to go through some kind of translation with getting a derivative really with respect to time, and we've been doing with respect to x, so we will change that a little bit. So notice the first part, and this is just about our notation. It wants us to translate this statement into calculus notation. And so for the first one, if you're talking about the volume of a cylinder is increasing at a rate of 6 cubic feet per second, then we would note that the rate of change of the cylinder is going to be, the volume of the cylinder, is going to be dV over dt, because our rate of change with all of these related rates, these are looking at how things are changing over time. So dV dt is going to be equal to 6, and then we have feet cubed per second. And so there would be the calculus notation for the statement that we're given. So for number 2, the depth of water in a rectangular pool is decreasing at a rate of 2 inches per hour. So here we're talking about the depth of the water, or really the height of the water. So to note how that is changing, we're going to say dH dt, and that h is for the height. And notice that it is decreasing, so we're going to make that 2, and we need to include our rate, which would be inches per hour. So we have inches per hour. So for number 3, at rush hour, the number of vehicles going through the Sun Pass toll booth is increasing at a rate of 85 vehicles per hour. So notice we're looking at the rate of change of the number of vehicles. So you can note that, however, I'll probably just use V for vehicles. So the number of vehicles going through, so we're going to say this is going to be dV dt is going to be equal to 85. And then again, don't forget your units. So we have vehicles per hour. And then with number 4, again, air is escaping a spherical balloon at a certain rate. So the air in that balloon, that is going to be talking about how the volume of that balloon is changing. So we're going to say dV dt is going to be equal to negative 15. And then we have centimeters cubed per, seconds. Okay, so now we're going to look at our formulas, and these are some basic formulas. Don't get so caught up in having to memorize them. Now, some of the more basic formulas, like area of a circle, volume of a cube, area of a rectangle, things like that, you do need to know, and most of you already know those. But if you don't, do keep in mind those are certain formulas that they will expect you to know. And some of the more complex formulas, they will give those to you. So when we talk about the area of a rectangle, and they want us to find the derivative with respect to time. So we're going to do the derivative of both sides. So the derivative of A is going to be dA dt equals, now over on the other side we have length times width, so we need the product rule. You have to use the product rule there. So we're going to have first times the derivative of the second. The derivative of W is 1, so it's going to be 1 dW dt plus second times the derivative of the first, dL dt. And now we have that formula. Gone ahead and found the derivative of that. Now for number 6, the circumference of a circle, you have to keep in mind that this 2 pi, That's just a number. It's the coefficient, so there's no product rule here. So do keep that in mind. There's no variable multiplied to another variable. This is just a number multiplied to r. So the circumference of a circle, that's going to be dc dt equals, and this is going to be 2 pi, just the coefficient there, times the derivative of r, which is going to be dr dt. All right, moving on to the next one, we're looking at the volume of a cube. So the volume of that cube, if we do the derivative with respect to time, we're going to have dv dt equals 3s squared ds dt. Okay, moving on to the next one. Now this one we do have product rule inside here. Notice 2 pi, that's just a number times r times h. So we will need to do the product rule, and I'm going to leave 2 pi sitting on the outside. So we have ds dt equals, and I'm going to keep 2 pi there, it just comes along with it. And now let's do our product rule. So we have first times the derivative of the second, which is 1 dh dt, plus second times the derivative of the first, which is 1 dr dt. And you can leave it like that because with all of these you will be substituting in values. Okay, now for the area of a circle, again, derivative of a with respect to time equals 2 pi r, and then dr dt. And then finally the perimeter. So if we do the derivative of the perimeter with respect to time, this is going to be just 4 ds dt. Okay, so continuing on with this, we do need to recognize that pi is just a coefficient. So I'm going to let that sit on the outside here. So when we do our derivative, we have dv dt equals, and I'm going to just do pi times, and now we need our product rule again. So we're going to have our first times the derivative of the second, and so that's 1 dh dt, plus second times the derivative of the first, so the derivative of r squared is 2r dr dt. And again, leave this because we will be substituting in values. All right, so let's move on. And again, 1/3 pi, that is all a coefficient. So we're going to have dv dt equals, and we have 1/3 pi times, and then we have our product rule again. So we have our first times the derivative of the second, plus second times the derivative of the first, and again we are leaving this. Okay, and we've got 2 more. So for this one, again I would leave that 4/3 pi, that's all just numerical values. So we have dv dt equals 4/3 pi times, and the derivative of r cubed, 3r squared dr dt. And finally, last problem here. Now this one's going to be interesting because we've got both x and y, but the whole dy dt thing does not change. So we're going to have 2x dx dt plus, and I know in the past we've written dy dt, but that dy dt, or I'm sorry, not dt, dx, was because we were doing the derivative with respect to x. Now we're doing the derivative with respect to time, so it's going to be 2y dy dt. And the derivative of 25 is 0. Okay, this next slide, this goes through some helpful hints. I'm not going to read this to you, you all can read. And so read through this. It does give you a couple of nice little hints to help you. Especially, well, all of these you'll see in some capacity on the AP exam, but especially right here, this usually is troublesome for people. if a person is walking toward a street lamp at a constant rate of 3 feet per second, then we know that the distance is decreasing. And notice how it is noted. And then the second part, if they walk away from the lamp, then the distance is increasing and the rate of change becomes positive. So do keep that in mind because that does tend to be troublesome for people. Now this is a guideline for solving these problems, and this is the first major application that we have for derivatives. So the first thing it really encourages you all to do is to come up with some kind of graph and label your quantities. And this is optional, but it does tend to give some kind of outline to organizing your information. And you need to write an equation involving variables whose rates of change are either given or are to be determined. And very important, number 4, using the chain rule, implicitly differentiate both sides of the equation with respect to time t. That is so important for us. And then after completing step 4, substitute the results in. And this last part here, this is the last step after you figure out what goes where. You will be substituting into the equations and solving for whatever you're asked to find. All right, let's do our first problem. And this one's just a general problem about x and y. You are told that you have x and y are both differentiable functions of t and are related by this equation. And they want you to find specifically dy dt given, and notice what all you're given. And so the first thing you will normally do after you've got all of this information, you've read through it, you're going to take some formula and you're going to find the derivative of both sides. So the derivative of y with respect to time, we're going to have dy dt equals, and that's going to be 2x, again, dx dt, minus 3 dx dt. Now that you have this, read through and see what values you know. You know x is 3, and you know dx dt is 2 when x is 3. So notice that you're trying to solve for dy dt, so we already have that set up on one side. So we have dy dt equals 2 times, and our given x value is 3. Our given dx dt value is 2. And then we have times 3 times 2 again. And so notice we find dy dt, we're going to end up with 12 minus 6, or we're going to have 6. And so as far as notation here, we really need to look at this. Let's go ahead and be practicing this as well. This is evaluated at x equals 3. That would be a better notation for that. Okay, for example 2, we have a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So, and again, these problems start out with, they're kind of intimidating. So we're dropping a pebble into water. And if you've ever done that, you see that you end up with rings moving outward. So if here was the pebble, then this would be growing outward. So that's kind of what's going on. We see that the area would be increasing, so I know I should end up with some kind of positive value. Now, what should we already know about this? Well, we should know, if we're working with a circle and we're talking about area, we should know that area equals pi r squared. That's something we should already know. And then we are given that the rate of change of the radius of the outer ripple is increasing at a constant rate. So we are given dr dt evaluated, or no, it's not evaluated, it's just given to us, is 1 foot per second. So that's something we're given. Now we need to find the rate of change of the total area after, and let's see, when the radius is 4, that's what we need to find, is the total area when the radius is 4. All right, so the first thing we need to do now that we have our information filled in, we know all of this stuff, then we need to first, we're going to find the derivative of what we know. We need to find that derivative. So we're going to have dA dt equals 2 pi r dr dt. Okay, and then notice that for the second part, after we have all of this, then our next step, and 99% of the time, would be to substitute in your given values. So now dA dt, that's what we're trying to find. Remember, that was what we needed to find. So we have dA dt equals, we have 2 pi, and then r we were told was 4, and dr dt we were told was 1 foot per second. And so after we substitute in and solve, then we should be able to have our final answer. So this is going to end up being 8 pi, and our units would be feet squared per second. Okay, example 3, air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? So the first thing we would need to know, the fact that we're talking about air being pumped into a spherical balloon at a particular rate, that's going to be the volume. So we need the volume formula for a sphere, so that's going to be 4/3 pi r cubed, and that would more than likely be given to you as far as on the test. Now notice what we're given is the rate at which the air is being pumped in, so that's the rate of change for the volume. So we know dV dt equals, and it's going to be 800 cubic centimeters per minute. And notice they want you to find the rate of change of the radius when the radius is 30 centimeters. So we need to find dr dt given r is 30 centimeters. All right, so again, going through our steps, the first thing we would need to do would be to find the derivative of that volume formula. So let's go ahead and do that. That's going to give us dV dt is going to be equal to, and if we multiply that 3 down, that's going to cancel with the 3 in the denominator. So I'm going to have 4 pi r squared dr dt. So there's our first step. And now our second step, just like the previous one, we need to substitute. Okay, so if we can substitute, let's see what we have. We know here dV dt, that was given to us, so that's going to be 800 equals, and we can put in our units or just leave them out. Either one would be fine. Let's go ahead and put in the units just for the practice of it, because it would help you keep straight and let you know whether or not you've got the correct answer. So that was 800 cubic centimeters per minute equals, and we have 4 pi, and then we're going to have r squared. And r was 30 centimeters, And so we're going to have r squared, and then dr dt is what they're asking us to find. And so here I wouldn't do a lot of multiplying out because things will cancel. Now 30 centimeters squared, that's going to be 900 centimeters squared, and that's what we're going to need to move over to the other side to solve for dr dt. So we can do a lot of that algebra all in one step, and we're going to do that to save some time. So we're going to have 800 centimeters cubed per minute, and that is all over 4 pi times 900 centimeters squared, and then that's going to be equal to dr dt. Now a lot of times with this being multiple choice is usually how you will see this type of problem. I wouldn't worry about multiplying stuff out because you can do a lot of canceling here, and that's what I want to do. So notice the zeros can be chopped off, and then notice 4 will cancel into 8, leaving a 2, and there we're finished with that. Now we do need to check our units, so numerator will cancel with that numerator. And so it looks like we're ready for our answer. And so the final answer for this is going to be, and I need to move my screen over, sorry. So dr dt is going to be equal to 2 over 9 pi, what's left in the denominator. And we're going to have with our units centimeters per minute. Our next problem is what I call a classic related rates problem. You have the top of the ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? So we definitely would benefit from a good sketch for this. So sketching this, we have a ladder propped up against the wall. So let's just very easily sketch in a wall, kind of a crooked wall for sure. And then we've got a ladder on this other side of the wall, and this ladder is sliding down the wall. So notice that here the ladder is moving downward, and this side we could label Y. And notice as the ladder is sliding down, then the base of that ladder is moving out. So we're going to call that side X. And we know that the ladder was 25 feet long. Okay, so there's a good picture of what's going on with this, and we will make sure that is perpendicular. So let's fill in some of our other stuff. So it's asking us what we should know. Well, we should know that looks like a right triangle, so we need to know our Pythagorean theorem. X squared plus y squared equals that other side squared, right? And we do know that side. That's going to be 25 squared, right? Something we should know. Do not multiply that out. Now notice that we also are given the rate at which the ladder is sliding down. So we know dy dt is going to be equal to negative 3 feet per minute. And we know it's negative simply because the ladder is moving downward. Okay, and then finally what we need to find, they wanted us to find the rate of change, the base of the ladder to the wall, that distance. So that's going to be a dx dt, and we need to find that when y equals 7, because that's how far from the base or from the ground we are. Okay, so got a lot of good information here. Now let's look at the derivative of our formula. That's always the first thing we're going to go do after we list out given information. So the first thing, let's find our derivative. So we're going to have 2x dx dt plus 2y dy dt, and that's going to be equal to 0 because the derivative of a constant is still 0. And so we have all of that information. Now we could go move and rearrange, or we can stop here and look at what are we asked to find? We are asked to find dx dt. So let's look at the stuff that we do know. I know dy dt, and I know a y value, but unfortunately we were not given an x value. So we're going to have to go back over to our drawing and see if we can't find some kind of x value. So let's see. We did know, we were given that y is going to be 7. So we could do the Pythagorean Theorem in order to find that missing side, or if you know your triples, this should be a 7, 24, 25 right triangle. But let's go through our Pythagorean Theorem. X squared plus y squared equals 25 squared, and this would be on the non-calculator. So you have x squared plus 49 equals 625, and solving this, subtracting over 49, taking the square root, x is going to be 24 feet. Now again, knowing your Pythagorean triples will save you some time because this work here you don't necessarily have to show. So knowing that other value will come out to be of some good use for sure. Alright, so now our second step, after we have all of this, our next step we need to go back and substitute. So that was always our second part of this. So in our substitution, we know, let's see, 2 times x, and we just found our x value to be 24, plus, and then times dx dt, dx dt, plus 2 times y, and y was 7. And then dy dt, the rate of change of this moving down the wall, that was -3. And all of that we're substituting in, and every bit of that should be equal to 0. Alright, so let's see what we have here. 2 times 24, 48, dx dt. That's going to give us minus, let's see, 6 times 7, 42 equals 0. And so very quickly from here we can solve this. So we're going to have dx dt equal to 42 over 48. And if this was free response, you could leave it, but it's probably going to be a reduced multiple choice. So let's see, what can we take out of both of those to reduce them? Looks like we can divide out a 6. So we're going to have 7 over 8, and then our units would have been feet per minute. Okay, for our next problem, we are given at noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the two ships changing at 4 p.m.? So let's draw a picture, and it does sound like, let's say we start at an origin, and ship A is out this direction, and ship B is going to be north here. Now with this, we know ship A, let's say A is out here, and it's 150, what were the units? Meters, maybe 150 kilometers east of ship B. And ship B, let's say, would be up here. And so looking at this, though, we have to keep in mind, even though we're 150 kilometers over, our ship A is sailing to the west. So ship A is heading this direction, so I know that this distance is actually shrinking. So we could label that side 150 minus x, and x is just because it's running parallel to the x-axis, and we're subtracting because I know that 150 kilometer distance is shrinking because we're told ship A is sailing west. Now we also know at 35 kilometers per hour, we know that that's going to be dx dt as well. That's how we're changing to 35 kilometers per hour. And then we're also told that we have another ship, and this ship is traveling north. So that distance is increasing. Now, I don't have much to go on with that, so I'm going to label this side y, but I do know the rate of change, and so I'm going to call that dy dt, and that one was 25 kilometers per hour. All right, so now what we're looking for is the rate of change of the distance between the two ships. So actually we're looking for this side over here, and y'all just pretend that's a straight line. It's best to get. So xy, we'll call this other side z just for grins. This is what the distance would be between A and B, and dz dt would be the rate of change of that distance, which is what we're trying to find. So let's see, this looks awful lot like a Pythagorean theorem type of problem, which it should be. So let's go back over and now let's fill in some of the stuff that we know. And we know x squared plus y squared is going to be z squared, but we know we don't have just x there. So let's go ahead and put in that, because that distance again is decreasing, it's going to be, not x, but 150 minus x, all squared, plus our y squared equals our z squared. Okay, and we are also given, what else are we given with this? We were told as well that our dx dt, we had two of those givens actually. We know dx dt is going to be 35 kilometers per hour. And we were told that dy dt is going to be 25 kilometers per hour. So that's good to know. And so they're asked to find the rate of change of the distances between the two ships. So according to what we have drawn, that's going to be dz dt. And we want to know what's going on with that when time is 4 p.m., which is really going to be 4 hours because we were told that these ships were starting at noon. All right, so what we've been doing with all of this is we needed to go ahead first and find the derivative of what we know. So let's go ahead and do that. If we do this derivative, now keep in mind we're looking at the derivative of this part here. So that derivative, we're going to have to do chain rule for that first one. So we're going to, our first step, we're going to multiply the 2 down times 150 minus x, all to the first, and then times the derivative of the inside. Plus, and then we're going to do the derivative. I almost messed up. I forgot my dx dt. I'm sure somebody's yelling at the screen telling me that. So it's going to be dx dt plus, And then we're going to have 2y dy dt equals 2z dz dt. So, my gracious, what an equation. There's at least a 2 in every single term. So, let's go through and simplify this a bit and mark out those 2's. We can drop that 2 from every single term. So, now that we've canceled out those 2's, I would go ahead and go back and do some more simplifying. So, that negative in front, I would say negative. And you can distribute this if you want to, that negative into each part, since the 2 has been canceled. So we would have negative 150 plus x, and then dx dt, plus y dy dt, equals z dz dt. Alright, so now we have our formula. The next thing we always did was to substitute in. So we do need to start plugging in some values. Plugging in what we know, it looks like we're probably going to run into an issue right here with z. And so we need that value because we are looking for dz dt. So let's go back over and see what we can do about finding those values. So it looks like from our triangle, we need to find really take the rate and multiply it by our time to get those side lengths. So for our first one, let's see when time was 4, because that's after 4 p.m. and we started at noon. So for our x value, if we take 4 and we multiply it to 35, that's going to give us 140. But now keep in mind we started 150 east, so really this side is going to end up being 10 kilometers. Now for the other side, we're going to go ahead and say 4 times 25. And that's going to give us 100 kilometers. So I know this other side up here, we have a length of 100 kilometers. So to find z, we're going to have to do the Pythagorean Theorem again. And so side z is going to be the square root of our side 10 squared. So that's going to be 100 plus, and then we're going to do 100 squared. So 100 squared, oh my, that's going to be 10,000, I think. Alright, so, gosh, this is non-calculator. Now, notice here before I put all of this together, I have 100 that's common. So I'm going to factor out 100. And notice what's left over is going to be 1 plus 100. And that makes that way easier because I know the square root of 100 is 10. And then what's left under is 101. So that was a nice little quick way to do that. So I know side z is going to be 10 on the square root of 101. Now, let's go ahead and fill in. I think we have all the pieces that we need in order to fill all this in. So, let's see here. I'm going to go ahead and, so for number 2, or the second step, let's go ahead and sub in what we know. And so here we knew after solving for our side, we had 140, but we knew that simplified down to 10. So substituting in that side length there, that was going to be 10. Well, actually negative 10. If we plug in here, that was 140, wasn't it? So negative 10, and we know the rate of change, dx dt, we know that's going to be 35. plus our y value, well, we found that side to be 100 times the rate of change. And that's going to be equal to our side z that we found, which was 10 square root 101 times dz dt, which is what we're looking for. All right, so let's see. We're going to have negative 350 plus 2500 equals 10 root 101 dz dt. All right, so let's combine those. And if we do, that's going to leave me with 2150. If I put those together, and then I'm going to divide by 10 root 101, that's going to leave me dz dt. And here, the only simplifying I would expect would be that, and so you're finished with it. Do leave this with the radical in the denominator. We do need units. Let's put in our units. Units would be kilometers per hour. So definitely include those units. Example 6, you have a right circular cylinder and it's changing shape. The radius is decreasing at a rate of 2 inches per second while its height is increasing at a rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? So we've got a few things going on here. We were told this was a right circular cylinder. So let's go ahead and sketch a picture. What's going on with this? So a right cylinder is like a Coke can, so to speak. And so we have a height and we have a radius that we're given. And we were told here, you've got the radius, and then we're going to have a height that we're going to drop. And so since it was a right cylinder, we know we have these right angles. And so we know the volume, and that'll always be given to us, so that's handy to know. We know volume is pi r squared h. And so we're given the rate of change of the radius. Notice dr dt, rate of change of the radius. And they said that it was shrinking, so that's a negative 2 inches per second. And we were told that the rate of change in the height, so dh dt, is going to be 5 inches per second. All right, and so now it wants to find the rate of change of the volume, or how fast the volume is changing, so dv dt, at, or when the radius is 4 and the height, I believe that was at 6. All right, so first thing, again, as usual, we need to find the derivative of our given formula. So that's the first thing we'll do. So our formula dv dt is going to be equal to, and I would leave pi just out to the front, and we have our product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. Okay, now the rest of this we are going to substitute in just like we normally do. So our second step, let's go ahead and plug in and see if we can't solve this. So second step, now dv dt is what we are looking for, equals pi times, now r squared, so r is going to be, we have 4, so that's going to be 16. Because we have r is 4, so r squared is going to be 16. And we're multiplying that to the rate of change of the height, which was 5 inches per second, plus our height, which we were given to be 6, times 2r, so that's going to be 2 times 4, so 8, and then times the rate of change of the radius, which is going to be -2. All right, and so let's see if we can't simplify this down. Now, if this was free response, you would leave it alone, but if it's multiple choice, you're going to have to simplify some. So let's see, we're going to have 80 minus 96, and so it looks like here we're going to have -16 pi, and it's volume, so it's inches cubed per second. All right, the last example that we're going to look at, and all of these have been classic forms of related rates problems. And this is going to be the inverted cone problem. So you're going to have a cone, and most of the time it will be inverted, but nothing says it has to be. And this cone, you're going to have two different variables in your derivative, and we really will want to try to eliminate one of those if possible through some kind of relationship between the radius and the height. So you're supposed to know this formula. Well, you're given the formula, so that's something you know. Volume is 1/3 pi r squared h, and we're given that the rate of change of the volume is going to be -1 centimeters cubed per minute, and it's negative because water is leaking. And they've asked us to find the rate of change of the height when the height is 3 centimeters. All right, so one thing we'll need to do is pull the triangle that we see built into this cone, this portion here. We're going to pull that out, and we're going to look at that and try to come up with the relationship between the height and the radius. Now, we were told that the diameter was 6, so that means the radius is 3, and we were also told that the height was 9. So if we break this into parts of a triangle, notice that as we move down the height, this radius will change with respect to this height here. So we know we can build some kind of ratio for radius to height, and that's going to be a 3:9 relationship. Now you need to go back and look. We are trying to find the rate at which the water level is dropping, so we're looking for DH. So if we're looking for DH, we need to get rid of all the R's in our formula so we don't have to find the rate of change of the radius. So to solve this proportion, I can multiply my H value over here to the other side. And so here I have R equals 1/3 H. So that's really a first step with all of these cones that we work with. Now our second step for this, let's go back over to our formula and let's plug in what we know about that radius. So our volume formula is going to be pi, and we had 1/3, it's 1/3 pi, sorry. That would look better to write it 1/3 pi times, and we have r squared, but we are going to substitute that r value in terms of h to make it a little bit easier. So we're going to have 1/3 h squared times h. So our volume is going to be this is 1/9 times 1/3, so 1/27 pi h cubed. Now from that, let's go ahead now and do the derivative because we have eliminated one of the variables, and that'll make it a little bit easier. So we're going to have, for the third part, dv dt equals 3/27, so that's going to be 1/9 pi h squared dh dt, and dh dt is what we're looking for. Okay, so let's substitute in now what we know, and so in doing so, we should have just dh dt left. We know the rate of change of the volume is going to be -1 equals 1/9 pi times our height, which our height is going to be 3, so we're going to have 3 squared, and then dh dt. And so here, 3 squared, that's going to cancel with 1/9, so we need to divide pi over. And so we have -1 over pi is equal to dh dt. And so we have found the rate of change of the height here. Oops, sorry. Do not box in anything, especially if it's free response.